when you want to convert this to frequency domain, it would be Fourier transform of this guy convolved with Fourier transform of this guy.
Two gate functions.
Oh. And when you convolve two gate functions,
don't you get the triangle?
you go through this.
It would be the triangle.
You already know how to convolve. This is easy. Even if you forget, you shift one of, since there is symmetry here, it's very easy. You shift one of them and you keep one constant and you move the one that is shifted as a function of time. So, and then you look at the overlap and then you multiply together. So when you're shifting it, you know, when the second one is, let's say, up to here, nothing happens. There is no overlap, so it's 0. But as soon as f gets smaller than minus 200, you see an overlap. So, and then this overlap goes up, 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 up till they both are completely overlapped. They give you maximum. And then you go in that direction, it reduces till it goes to 0. So when you look at the convolution, it would be something like this.
Because the inverse of the sinc squared is the triangle, right?
The what?
Oh, because I think there's a part, like you can go straight. Well, yeah, it's fine. I think it makes sense.
By the way, I'm ignoring these magnitudes, but you cannot. So.
Okay.
Any questions? Also, in chapter 7, we discussed PCM, PPM, whatever, PDM, and so on. But all of them, we had to have sampling, and we discussed sampling frequency that has to be at least equal to the Nyquist rate. But we always prefer sampling rate to be higher than Nyquist rate. Let me ask you this. If you have a signal, looks like this in the frequency domain, or any other shape, I don't care about the shape, but it's band limited to B. Okay, and you sample this signal in time domain. Let's say this is x of t, x of f, I'm sorry. And you sample this signal, that's ideal sampling, you use impulses to sample. What would be what would be the Fourier transform of the sample signal? This signal in the time domain would be like a sinc square, whatever it is. But when you sample that sinc square, you get a sampled version of sinc square. What would be the Fourier transform of that sampled signal? How does it look like? Don't know. Again, let's say this is frequency domain, but let's say x of t is a sinc function, right? And we sample this x of t with some sampling frequency. So that sampled version has Fourier transform. We call it x of s. What is that Fourier transform? How does it look like? If you take basic communication, you have to answer this. It's going to look like this, but repeated. So it's going to look like this.
That would be for that one, right?
That would be for sampled version of this guy.
Okay.
Sampled version in time domain. Okay. This signal is in the frequency domain. If you look at it in the time domain, it's a sinc square. And if in time domain you sample that signal, you're going to get a Fourier transform for the sampled version, something like this. I want you to understand the Nyquist rate, why Nyquist rate is at least 2 times B. So it's going to look like this. But what are the locations here? I'm giving you a hint. The sampling frequency is f sub s. Fs, this is at 0. This is at Fs, 2Fs, 3Fs, and so on. So I sampled that signal with some random sampling frequency of Fs, and this is the result of the sampled version. This frequency is B, right? This frequency then is Fs minus B. So when you sample this signal, you want to make sure you are not damaging your signal. Because if this is the spectrum of the sample version and you want to get your original signal back, all you have to do is put a filter here and get everything else rejected. So in order to avoid distortion, these 2 points, they should not overlap. So Fs minus B has to be at least greater than or equal to B. So that's why we get that Nyquist rate of 2 times B, because, but if you really sample it, never go with 2B, you always leave some room. So you go with sampling frequency a little bit above 2B. So that will give you this gap here, so they don't overlap. So, for digital communication, the first thing you need to do is to sample your signal. And then for PCM, first thing you have to do, sampling frequency has to be greater than or equal to 2 times B. And then after you sample it, you quantize your sample values. And we already went through quantization. After you quantize your sample values, each quantized sample will be converted to a series of symbols. In the binary case, your symbols are 0s and 1s. So you have a sampling frequency, and each sample is quantized and then converted to, let's say, R number of bits. So you're transmitting these symbols. So your symbol rate would be R times Fs, whatever Fs is. Fs is your sampling frequency. So that's something you need to be aware of. Let's say we have a signal, M of t. This is a message signal. Okay? It has a bandwidth of B. We don't know what this signal is. It can be video signal, it can be any signal. It looks like this. Sorry. I put these errors on purpose. Nobody says anything. So the signal in the frequency domain looks like this. Okay? And we want to transmit this signal using PCM. So we sample the signal with frequency Fs, and then we convert each sample to bits, let's say. We want to transmit it in binary. And then we create a series of bits per second, and we transmit. Let's say after you do all of this, you achieve a bit rate of 4 megabits per second. You're transmitting this signal in PCM format, and you are transmitted with 4 megabits per second. And you already know each sample, you have, let's say, 10 bits. So you're transmitting this signal, PCM, and you want to transmit it over a channel with a rate of 4 megabits per second. And your samples are converted to 10 bits each sample. One thing we want to know is what would be the maximum bandwidth of this signal that you can transmit. The channel can transmit 4 megabits per second, okay? And we already know when we sample the signal, we convert each sample to 10 bits. What would be the maximum bandwidth of this message that we can transmit through that channel? Definitely, if this signal has a bandwidth of 1 gigahertz, you cannot transmit it PCM over this channel. Hello? I told this everybody that for the exam you need to be here early. Please. Okay. So definitely we cannot have a signal with a bandwidth of 5 gigabits transmitted over this channel. Why? Because when it is 5 gigahertz, you have to have a minimum sampling frequency of 10 gigahertz, and each sample converted to 10 bits, right? So 10 times 10 is 100 gigabits per second. Definitely you cannot transmit it here. It's too small. So in this case, we want to know what would be the maximum of bandwidth of this signal that you can transmit. How do you approach this problem? Yes, first thing you need to do is to find your sampling frequency. If you know each sample is converted to 10 bits, and you know your bit rate is 4 megabits per second, so your sampling frequency is 4 megabits per second over 10 bits. So your sampling frequency is 0.4 megahertz. And we know sampling frequency has to be at least twice as this bandwidth. So the minimum bandwidth of the signal is equal to half of this, 0.2 megahertz. So your signal can have bandwidth all the way to 0.2 megahertz. and you can transmit it over this channel PCM. But if your signal bandwidth gets bigger than this, then this channel cannot handle it. Any question?
That's supposed to be bandwidth maximum.
Ah. Thank you. Again, all of these are really, really simple, but I still don't know if you understand it or not. Sometimes I think I explain simple things too much, and some of the faces look so bored. Okay. The other thing we discussed was quantization noise. You remember quantization noise? Because you had to assign certain values to each sample. Either you add some value or you deduct some value from your sample in order to have that sample to be equal to one of your quantized level, depending on how many symbols per sample you want to have. So that adding, subtracting adds a noise. We called it quantization noise. And quantization noise power was equal to this. Who can explain this? You guys just copying, and then you have to know what you are copying. We discussed quantization noise. Average quantization noise power was equal to this. Or what is this? Anyway, R was the number of bits per sample. M sub max was maximum value of your signal. So if you want to calculate signal to noise ratio of quantization noise, you have your signal power all over quantization noise power, and you get your signal to noise quantization noise. And we also went through an example if m of t is equal to a sine wave, a cosine of omega t. If your signal is a sine wave and you want to convert that to a PCM, so how can you get signal to noise ratio here? In general, this is signal to quantization noise. Any signal m of t with average power of p and quantization noise, which is related to maximum signal power value and number of bits per second. So if m now is a sinusoid, what would be signal to quantization noise? Well, again, you just follow this, my friends. Give me the answer then.
Would it be 1/2?
1/2?
A squared.
A squared, excellent. Because that's your average power. Divided by this guy, but what is this guy?
1/3.
What should I use instead of m sub max squared?
A squared.
A squared. Very simple, isn't it?
Yeah.
And and then you can simplify it any way you want. So